Hey guys, this is JP from Planning Seeds Tutoring. In this video, we're going to be talking about periodic table and its trends. And don't forget to use my referral code JPMon20 to receive 10% off on your next tutoring package. So before we discuss the periodic table's trends, and we're going to start off by just looking at the periodic table and how it's denoted. So first of all, there are 7 periods and 18 columns or 18 groups for within the periodic table alone. So each period, which is going to be denoted by the rows 1, 2, 3, 6, 7, these denote the number of shells or energy levels that are found for an atom. So hydrogen is going to have 1 energy shell, 1 level. Germanium is going to have 4. We also have groups. Our groups are going to be like our columns. We have 18 of these columns. These are going to be like the main ones right here. On our far right, group 18 is going to be known as the noble gases. Group 17 is known as the halogens. Group 16 is known as the oxygen family or the chalcogens. Group 15 is known as the nitrogen family, on and on and on. And group 1 is known as the alkali metals, except for hydrogen. But group 2 is known as the alkaline earth metals. Now between group 3 and group 12, this entire section is known as the transition metals. And within the transition metals, as you can see, there's like an expanded region right here, the lanthanide and the actinide series. These are known as the inner transition metals. Transition metals generally have very, very similar properties. They're all metals, and except these inner transition metals are just radioactive in addition to being normal transition metals. On our far right, we generally have our nonmetals in addition to hydrogen. Between our nonmetals and the transition metals, we have our metalloids. I'll also include aluminum here, but most of these other guys, so metalloids, they share different properties that are similar between both nonmetals and metals. Mostly everyone else are going to be just metals. Alright, how do we read this? Well, this image right here kind of gives you an idea of how you're supposed to read an atom and stuff. The name of the atom is given at the bottom. The symbol of the atom, which is always going to be capitalized for the first letter, and any other letters are generally maximum of 2, and that's going to be given by a lowercase. Symbol, name. The atomic number is the number of protons. And can also be denoted by the letter Z. The atomic weight here, or the atomic mass, it's kind of a little misleading, that term. This right here actually gives you the average weight of all of the oxygen that you can find around the world. In general, oxygen could be about 16 grams. You might find an isotope that weighs about 15 grams for 1 mole specifically, not one oxygen itself. It's an entire mole of the word. But it's just like a weighted average. Alright. Now, let's go back out into the image right here. Now, we just witnessed like an image of reading the periodic table based off of an image like this. And we know that's going to be our number of protons, or our atomic number. This is going to be our name, symbol, and finally the average atomic mass. Well, On this image though, you're not given the average atomic mass. Instead, you're given the Z value. So also denoted this way. That's the Z value, or the atomic mass, or the atomic number, which is the number of protons. And this is going to be the atomic mass, or the mass number. And this mass number is always equal to the number of protons plus the number of neutrons. And that should kind of give you an idea of like how many neutrons there are. Since you would always know what the number of protons is, you should be able to figure out the number of neutrons from that. Number of protons is always constant for any element. Always supposed to be the same number. Neutrons change based off of an isotope. If you have two different atoms with two different numbers of neutrons, they're called isotopes of one another. If you have two different atoms with different numbers of electrons, they're called ions. But they're always going to have, to be identical, you need to have the same number of protons. All right, let's get rid of this. All right, now before we look into the trends specifically, we do need to recognize some terms. We're going to need to recognize the fact that electronegativity is the ability for an atom to attract pairs of electrons. So for example, oxygen is known to have a very, very high electronegativity. Fluorine is known to have the highest electronegativity of all elements, and that's because they're able to attract more and more. They're able to attract electrons in an uneven way, as opposed to metals and stuff which don't really attract any electrons at all. Electron affinity is going to be the amount of energy that's been released when an atom gets this is supposed to be when an electron gets added, not when an atom gets added. Yeah, so this is going to, electron affinity is going to be the amount of energy released when an electron gets added, and it's going to be very, very similar in terms of its trend to the electronegativity trend. It's just you're going to be obviously releasing more energy when you add more electrons. That's it. Ionization energy is going to be the amount of energy that you need to remove an electron from the valence cell, or the outside shell of an atom. Finally, the atomic radius is going to be the distance between the distance between the two nuclei of two bonded atoms, identical atoms of the same element. All right. Now let's try taking a look at how these trends would kind of follow along in a map like this, in the periodic table itself. If we were to look specifically for electronegativity generally increases as you go higher up in the, I'm going to use electronegativity to be blue. It's going to be electronegativity. Yellow is going to be my ionization energy. And red's going to be my atomic radius. Just the trend lines overall. And green could be my electron affinity. I'm going to notice that electronegativity, ionization energy, and electron affinity are going to all have these exact similar trends. They increase as you go higher up in the priority table, and they also increase as you go further right. However, helium, neon, argon, they do not show an electronegativity. They have nearly essentially zero electronegativity, so they're not really part of it when it comes to electronegativity. Fluorine is going to be our highest electronegative atom. Electron affinity, exactly the same in terms of go up and to the right. Now, ionization energy, while it also has the same exact trend, a major difference is the fact that it does not have, I mean, helium is going to be it's the highest value in terms of the highest ionization energy. That's because helium does not ever want to give up its electrons. If you're a noble gas, you would not ever want to give up your electrons. Finally, atomic radius, though, is going to be the one trend that's going to be going the exact opposite direction. So atomic radius increases as you go further down, and it increases as you go further to the left. Now, the reason as to why this increases is because the more atoms you add, or the more protons you add, the more positive charge you have, causing more electrons to get attracted to the center. However, as you increase the number of shells, this is shell number 7, well, you're just making it bigger and bigger and bigger. Alright, that essentially covers up all of the major trends that you kind of need to recognize for the periodic table and a basic understanding of the periodic table. Hope you guys learned something new, and that's it. Thanks for watching.